Okay, so good evening to all of my fellow, students. Today we are in the second lecture of functional materials, and in it we'll be covering energy materials, battery and supercapacitors. As you can see, it's part 2. So I'm Dr. Dimple P. Datta, Associate Professor HBNI, and I'll be taking this class for you today. Sorry. So there's a problem on this side for the slide changing. But anyway, for today's class, the overview of content as I have given on this particular slide, you can see it is anode materials for LIB. We'll do a little bit of cell characterization. So when you have a lithium ion battery cell, how do you characterize that cell? So there are various techniques for that. So in it, you have cyclic voltammetry, which we'll be discussing. We'll be talking a little bit about impedance spectroscopy. This will be followed by charging discharging cycle. Then it's going to be a little bit about battery life. And with this, we will finish off our battery portion. And the remaining portion of this particular lecture, we'll cover a little bit on supercapacitors. And we'll also cover a little bit on the concept of fuel cells. So with this, let's move into the topic, the first topic which I'm going to discuss today, which is anode materials for LIB. If you remember in the last class, that is in the first class of energy materials, we had talked about different concepts, the basic concepts of electrochemistry, and then we had followed it up with the different kinds of primary and the secondary cells which are available. The primary ones which are non-rechargeable, whereas the secondary ones which are rechargeable, of which we have covered the different types of the batteries which are in vogue or in the market. And then we have covered about lithium-ion batteries and particularly the cathode materials. Because we are talking about materials, we are more interested in the material chemistry. And so we spoke a lot about the cathode materials for LIB. So today we will be doing the remaining part, which is the anode materials for LIB. There's some problem with the slide changing. Oh. Okay, thank you. So fine. So now regarding LIB anodes, commercial lithium-ion batteries, as I said, the cathode part is well established. We have LiCoO2, which is basically a layered cathode material. And there are other cathode materials also like the olivine structure, which I had discussed last class, and also the spinel structure. In the anode part, initially it started all with a lithium metal, but because of the problem of the dendrite formation, and the other various safety issues which rises because of the formation of these dendrites. So we had to go for a better option, and this better option was graphite. So why graphite? Because graphite, it has an operating voltage which is close to that of lithium and lithium plus, which is around 0.1 volt. If you remember last class, I had told you that the potential of the anode should be as low as possible. So the potential is very low, whereas the chemical potential is very high. So those are the ideal kind of materials which you will look for when you talk about anodes. So this space, graphite beautifully fits in because the potential which you have is around 0.1 volt. And then the capacity for lithium in graphite, it is around 372 ampere hours per kg. And how this is calculated? The thing is that when lithium is intercalating into the different layers of graphite, you have an insertion of 1 lithium per 6 carbon atom, and it gives rise to an intercalation compound like LiC6. And so if you consider LiC6 as the thing which is being formed when lithium is moving into the graphite, the specific capacity, if you calculate the theoretical specific capacity, it is around 372 ampere hours per kg. This is as per the theoretical capacity formula which we have already discussed in the last class. So far so good. So what is the problem which we have with graphite anode? Not much. Only thing is that if you remember, I had told you that the chemical potential of the cathode and anode has a limitation. That is, the limitation is given by the electrolyte HOMO and LUMO level. So although the redox energy of graphite, it lies above the lowest unoccupied molecular orbital, as you can see over here. So if you look into this LUMO level and if you look into the graphite level, you will find that the graphite is not lying lower to it. In fact, it is lying higher than the LUMO level. So it is having a potential which is higher than the lowest unoccupied molecular orbital of your electrolyte. So now what is going to happen? If this is the case, then there is going to be the formation of a SEI layer. So what is that? That is the solid electrolyte interface layer. Why? Because your electrolyte which is there is going to get decomposed. So if it gets decomposed, it is going to form a solid electrolyte interface layer on the graphite surface when it is in reaction with the electrolyte solvents. And because this particular SEI layer is formed, definitely there is going to be some loss of lithium because the lithium is coming in from your cathode and the cathode has a particular reserve of lithium. LiCO2 has this much of lithium. So out of which some of the lithium is going to get, you cannot use that lithium because it is getting, it is giving that irreversible reaction of formation of the SEI layer. So that much amount of lithium cannot shuttle back into your cathode. So that is lost. So you will lose a little bit of the capacity. But on the other hand, as you remember in the last class, we had mentioned that SEI layer formation has certain advantages also. And what are those advantages? The advantages is that the lithium ion can move very easily in that SEI layer. So that is the advantage which you have. And it also provides a stability for a longer cycle life because it prevents further deterioration of your anode or the graphite layer. So that is why SEI formation has some good points and the bad points, and together with it, graphite looks to be a very good anode for lithium-ion batteries. Now, if you look into this other diagram which I have shown over here, the voltage versus capacity, if you look into graphite and if you have the SEI stabilization layer which is marked over here, so electrolyte stability window where there is no SEI formation, in between this if you look into it, what you find is graphite is definitely lying below the SEI stabilization layer, and also its capacity is little bit less. With capacity, if you see, it's around 372 ampere hour per kg. So there are certain other other anode materials which are considered, which definitely can lie in between this SEI stabilization of the electrolyte window, the electrolyte stability window. And for this, you have something which is lithium titanate, Li4 Ti5O12. So this has a spinel structure and this lies within the electrolyte stability window, and it doesn't lead to the formation of any SEI layer. So with no SEI, there is going to be a very negligible volume change which is less than 1%, and so this lithium titanate, it offers a very long cycle life. So that is the advantage part of lithium titanate. So definitely then why in the commercial LIB you are not using lithium titanate? The problem is that the operating voltage of lithium titanate is low, as you can see over here, because lithium titanate, the voltage versus Li plus, as you can see, it is much higher compared to that of graphite. So there is a loss. And so this operating voltage is only 1.5 volt versus lithium and lithium plus, whereas what we need ideally for any anode material is that it should be as low as possible. So here graphite, which is having a voltage of 0.1 volt, definitely scores over a lithium titanate. And then the capacity is also limited. Here the capacity is only 160 ampere hour per kg compared to 372 ampere hour per kg what you find for graphite. So ultimately, these problems, what it leads to is that it reduces the cell energy density drastically. So because of this, it doesn't find much application in case of lithium-ion battery cells, which you are using for portable electronics, because for portable electronics, we are more concerned with the energy density. And it's here that lithium titanate cannot really score much. But lithium titanate can be very much employed in battery cells, in coin cells, and in batteries, which can be, ultimately used for grid storage. So renewable grid storage energy, their energy density is not a point of concern. in that particular kind of, in those applications, lithium titanate can have a lot of application as anodes for lithium ion battery. So now, of course, there are different things which affects the electrochemical potential. And among this, there is some effect of structure which we need to consider. Now, lithium titanate as such, as I said, that the capacity is low, around 100 and as you see over 160 ampere hour per kg. So how can we improve this capacity? So there are certain ways which you can improve it. Lithium titanate also has a very low electronic conductivity. So that also has to be worked upon. So now what are the different ways in which you can improve this particular material? So one is by changing the microstructure of this material or the nanostructure of the material. So if you do nanostructuring of lithium titanate, what happens is you enhance the reversibility of the lithium ion insertion and extraction reaction in the nanostructured electrodes without destroying the crystal structure. Why is it so? Because when you are moving into a material in its nano form, it has more strain bearing capacity. So when your lithium ion is getting inserted or deinserted from this particular material, what happens is that the strain, because it has more ability to withstand the strain, so the reversibility of this particular lithium insertion and deinsertion, it is kind of improved. So compared to the bulk material, when you move into nanostructures, what you find, there is an enhancement in the reversibility of the lithium ion insertion and extraction. Then again, because the size is small, you're moving into nano dimensions, nanometer dimensions, what happens is that there's a reduction in the diffusion or transport distance of the lithium ions and electrons which accompany the lithium ion insertion and extraction reaction. So the diffusion distance is decreasing. If the diffusion distance is decreasing, then definitely the kinetics of the process is going to improve. So obviously you are going to get a better effect on the electrochemical performance of this material. Then the third point which you have to know what are the benefits of nanomaterials is that there is a change in the site energy of the lithium ion which occupy the host lattice, and this affects the electrochemical potential of the electrodes. So what do you mean by this site energy? Site energy is nothing which is but the enthalpy. The Gibbs free energy has to be as minimum as possible, and Gibbs free energy, one of the major points which affect the Gibbs free energy is the site energy. And site energy is nothing but dH by dN, where N is the intercalating ion which is going in, the number of the intercalating ions. So this dH by dN value is nothing but the site energy, and the site energy change which is there in case of nanomaterials, this is more advantageous to have a better electrochemical potential of the electrodes. So then there again another way in which you can improve the capacity, the theoretical capacity of any material is by introducing defects. So how you can introduce defects in also control of the synthesis methods. So what does the doping do? So alien atoms or heteroatoms, they will replace the inherent atoms which are there in the host structure, and they are going to produce cation or anion vacancies, and this is going to affect the electrochemical performance of the electrode. Due to the modified chemical pressure, there is a lattice distortion or change in the crystal field, and all this is going to affect the electrochemical performance. So now take a small example. Here I've given an example. So suppose you have vanadium oxide. So this had a particular kind of specific capacity, as you can see when you are plotting the GDC or the galvanostatic charge discharge. You will find that this particular vanadium oxide, it is having a capacity of around 225. The moment you are doping in nickel into this vanadium oxide, what happens is there is an increase in this capacity. It is going up to almost 275 milliampere hour per gram. So what is happening? So when you are putting in a nickel which is having a lower valence compared to that of the vanadium, to maintain the electroneutrality, the oxygen vacancies are produced, and this will play a role in the nucleation for phase transitions, which benefits the rate capability of this particular electrode material. So the lower valence of the nickel in place of the high valence vanadium, it can effectively decrease the electrostatic repulsion between the cations, and thus it will decrease the lithium site energy, as I mentioned before. And if you decrease the lithium site energy, then it is going to increase the potential of the doped material. So you are decreasing the lithium site energy, you are increasing the potential of the material, the chemical potential of the material. So that kind of helps. So that kinds of help because you are increasing the chemical potential, which means that the anode voltage is going low. If it is going low, then if you are putting that kind of anode in a lithium ion battery, your effective voltage is nothing but the voltage of the cathode minus anode, and so obviously that voltage is increasing, and so your battery's voltage increases, and that means the energy density increases, because the energy density is nothing but it is a factor of, it depends on your specific capacity, and it also depends on the voltage. So then there is another thing, that is the effect of the amorphous state on the electrochemical potential. What do you mean by amorphous state? There are many things which are not crystalline. They are more amorphous in nature. These are mesoporous materials. So they are very conducive to the full infiltration of the electrolyte. What happens if there's an amorphous material? Then the electrolyte is able to invade into the material. So definitely if the electrolyte is moving in, so the conduction of the lithium ion from the electrolyte via the electrolyte to the anode, it becomes much more easier. So it reduces the migrating distance of the lithium ion. It is facilitating the lithium ion exchange across the interfaces, and it is able to tolerate the large volume change of the electrodes due to the lithium insertion and extraction. So what happens? These factors greatly enhance the lithium storage kinetics and the structural stability of the material. But you have to remember that this is not a very good solution, because if so much amount of electrolyte is coming in contact with your anode, it is going to lead to the formation of lots and lots of SEI. And if too much of SEI forms, what happens is ultimately you lose lithium, because it is an irreversible reaction. Always remember, SEI formation is an irreversible reaction, and a battery's capacity will increase only if you are having more of reversible reaction taking place. Otherwise, there is going to be a loss in the capacity with repeated cycling. So there is going to be, the balance has to be there. So if you take a completely mesoporous, a completely amorphous material, then that SEI formation is going to decrease the capacity. So there is going to be a balance between the mesoporosity or the amorphosity of the material which you have and its crystallinity, to have the ideal kind of electrochemical performance which you are looking for or which you want in your anode materials. So what is the current status of lithium-ion batteries presently? So what we have right now in the commercial lithium-ion technology, this is limited to a gravimetric energy density of around 250 watt-hour per kg, and the volumetric energy density is around 650 watt-hours per liter. And what is the target? The target is high. So you have around 500 watt-hours per kg, and the volumetric capacity should be around 1000 watt-hours per liter. So how do you do that? As I said, you can increase the cell voltage. How do you increase the cell voltage? Then what you have to do is you have to improve, you have to work on better materials. You need cathode materials which will operate at a much higher voltage. So the cathode surface with operating voltages which is greater than 4.3 volt, the problem is that it is not stable when it is in contact with the organic solvents which are present in the electrolyte. The electrolyte is having a salt, a lithium salt, which is normally LiPF6 or LiClO4. But you have it dissolved in organic solvents like EC, DEC, DMC, etc., which are used in the electrolyte. Now the problem is that if you are having a cathode which is having a very high voltage, operating voltage, as I showed you, the stability window, it is going to be above the stability window, and so ultimately it is going to lead to a decomposition, and that decomposition of the electrolyte is going to result in the formation of an SEI layer which you don't want. So there are different potential candidates which has been identified, which has higher operating voltages, and these are spinels like LiMn 1.5, Ni 0.504, which has operating voltage of around 4.7 volts. You have olivine lithium cobalt phosphate around 4.8 volts, and there are of course the layered NMC kind of cathodes which has an operating voltage of greater than 4.3 volt, and which are able to reversibly extract and insert more lithium. And of course, another way of increasing the cell voltage is definitely you have to work more and more on the electrolytes, new liquid or solid electrolytes, which will be able to withstand the high voltage cathodes. The other way is of course increasing the charge storage capacity, and how you can do this. That this capacity, see when we talk about graphite, it is limited by the capacity of the insertion or deinsertion of the lithium ions in between the crystallographic sites, okay, which is available for the reversible insertion and extraction of lithium. But the other kind of electrode materials which we have, that is the conversion reaction electrodes, they do not have these kind of limitations. But the biggest problem with conversion anodes are that they have a very high volume change. What are the conversion reaction anodes? Like all the oxides, the sulfides, the selenides, these are all conversion reaction anodes. So whenever this kind of anodes are used, the major problem is that though they are not limited, the capacity is very high, because that N value, instead of being 1, which you find in case of graphite or the insertion materials, that N value, the number of lithium which transfers, that is much more than 1. So obviously the capacity increases, but the problem is that there is a very huge volume change, sometimes up to around 400%. And if that is the case, then in that case, what is going to happen that when you are pasting it on your current layer, on your on your current collector, it's going to peel off from the current collector and it's going to lose contact. So that is why adjusting that volume, it becomes a big problem. So what are the different methods which are tried? You have to either reduce the particle size to nano size, or deliberately you have to leave space within the active material architecture, so that there is, basically there is enough volume available for the material to expand. But what happens, what is the downside of this? That it will increase your ACI formation, because you are increasing the porosity of your material, and it is also going to decrease the volumetric energy density, which you don't want. So currently the only progress which has happened in case of anode is you incorporate a little percentage of silicon into graphite to increase the charge storage capacity marginally in all these practically used commercial lithium ion cells currently. That is the change which has happened. And what you can see that where this lithium ion technology is headed is basically you have to work on insertion reaction cathodes and anodes. This will continue obviously for the foreseeable future despite the limited energy density. But the thing is that it has a lot of stability. So then obviously it is going to be used for quite some time now. And much of the effort currently is towards conversion reaction anodes and cathodes, because they offer up to an order of magnitude higher capacities than the insertion reaction electrodes. But their practical viability is met with a lot of challenges because of that volume expansion problem. And then you have a renewed interest in employing lithium metal as an anode and replacing the liquid electrolytes with a solid electrolyte. But this is a very, very recent field of research, because it can definitely offer safer cells, because if you are not having a liquid electrolyte in this case, and it can also operate at higher operating voltages, and it can have more charge storage capacity. But the practical viability is still we have to cover quite some distance in research to achieve that kind of practical viability. So a feasible near-term strategy for researchers in this field is to focus on high nickel layered oxide cathodes, liquid electrolytes which are compatible with and form stable ACI on both graphite anode and high nickel cathodes. And then innovation in cell engineering to fabricate thicker electrodes and reduce inactive components. So basically if you have what are the inactive components in a particular battery? Because if you're having this anode material, you have to paste it, right? So you have a binder, then you have some kind of conducting agent which is being added, because most of these materials don't have enough conductivity, electronic conductivity. So you have to add some kind of carbon material as a conductant. So these all don't, ultimately they don't contribute to much to the capacity. So they become inactive components and they increase the weight of your battery without actually taking part in the electrochemical process. So that has to be reduced. And so the novel system integration should be towards to realize a safer, long life and very affordable system. So if we look into it, what we have right now is the usual process where it's the insertion materials which are ruling the roost, because though it has low capacity, but the volume change is quite acceptable in this case, and that is why this technology is quite well established and it is commercialized. Whereas when you look into the alloying and the conversion metals, which are the other kind of materials which you can use for anodes, in this case, though it has a very large capacity, the volume change, as you can see from here to here, it is huge. Similarly, for the conversion materials, you have a large capacity, but there is a lot of voltage hysteresis which is taking place, and there is also considerable amount of volume change here. So at the end of the day, what we see is we have to kind of ultimately what it looks like is we have to kind of mix and match, and we have to find ways to circumvent these problems and to enhance the properties which is going to give you a positive effect in the electrochemical performance of these materials. So parameters that needs to be considered whenever you are looking for materials for battery. So for electric vehicles as well as for portable electronics, it is the energy density which plays the maximum role. As you can see, we have given a double tick for that. Whereas for grid energy storage, energy density is not that very important, but cost, cycle life and safety are important for all the three applications, and it is desirable to have a very fast charge discharge rate for all the three applications, because the time which is required for charge and discharge for the charging of your battery, it should be as low as possible, right? You cannot take up a battery for anything if it takes 24 hours to get charged. So you have to have a desirable fast discharge, charge and discharge rate for all the different applications. So how do you fabricate? I spoke so much about materials, so now you should know how the fabrication of this coin cell is done. So in a coin cell, what you have, this is a CR2032 kind of configuration. The coin cells which are normally being used, the materials are tested in this kind of cell configuration mostly. 2032 is nothing but the dimension of this particular coin cell. So what you have over here is a negative case. Then you have a wave spring, which is nothing but the thing which is going to prevent the touching of this spacer with the negative case. Then what you have is the cathode material, as you can see over here, which is in pink. Then you have the separator. Then you have a lithium reference. This is the wire for the potential. Then you have a graphite anode, and then you have the positive case of the battery. So this entire thing is kind of clipped in. So you prepare the graphite anode, then you prepare the lithium, manganese spinel, the manganate cathode, and then you are having the separator. You are putting in the electrolyte, is a drop of that electrolyte is added into this separator, and then you're clipping it, and ultimately you are putting it into the battery tester cycler for further studies. This is for the coin cell. Then you have something which is known as the bigger variety or the larger variety, which is a pouch cell. So for that, what you do is this: when you have the material, first you will homogenize that particular material. You will add a binder, like it can be a PVDF, or you can use other kind of binders like carboxymethyl cellulose, CMC kind of binder. If you are using PVDF, you will use an organic solvent like NMP, N-methylpyridinone. And then you have some extra solvent and additives which is added. Additives are mostly the conductive additives like Super P or carbon black. So these kind of conductive additives are added. And then you are coating it. You're coating it with a doctored blade. And then you are doing some kind of, or you can do a slot die kind of method, or you can use a screen printing. And then what you do is calendaring, because you have to kind of press the material, because this particular spreading should be as even as possible, because if the spreading is not even, if you have some uneven surfaces over there, it develops kind of hotspots, and from there your dendrite formation can take place. So that you have to avoid at all costs. Then you dry this, because you have all these solvents, you need to dry, and then you are preparing the pouch cell. So this way your material is there, and this on the thing on which you are spreading this material is nothing but your current collector. So the current collector can be copper, or it can be aluminium foils, depending on whether you are making an anode or whether you are making a cathode for lithium-ion batteries. So now our cell is prepared, whether it is a coin cell or a pouch cell. Now we come to the next part of the lecture, which is your cell characterization. So how will you do the cell characterization? So for this, we have a few techniques. We have cyclic voltammetry, which we normally do. And then you can also do something which is known as electrochemical impedance spectroscopy. So first we will discuss today the cyclic voltammetry. So first let's see what is cyclic voltammetry, and then we will apply it to battery materials. So it is a very commonly employed technique to investigate the reduction and oxidation process in molecular species. And it is an invaluable tool, to study the electron transfer initiated chemical reactions. So there are two conventions by which you show this plot of current versus your potential. So in one case, what you have is you go from the high potential to the low potential. So the top part is the reduction and the lower part is the oxidation, and this is the US convention. Whereas the IUPAC convention, which is normally used nowadays in most of the journal publications, it is you move from the low potential to the high potential. The bottom part is reduction and the top part is your oxidation. So the arrow over here, it indicates the beginning and the sweep direction of the first segment or the forward scan, and the caption indicates the condition of the particular experiment. So here, as you can see, it starts from the high potential and it moves to the low potential in all cases. Only the convention, it differs. How you're representing it, it differs. So very simple example, let's take and find out how the CV is going to look. So you have, suppose you are doing a reduction of the ferrocenium and you are reducing it to form ferrocene. So FeC plus electron giving you Fc. So here in this case, what we have used is, as you can see, we are going from a high potential here to a low potential there. So this particular example is in the US convention. So what you have over here initially, the top part, if you remember in the previous slide, what we have shown is the top part is the reduction reaction, what is happening. So in this reduction reaction, if you look into this different plots, like what is the concentration of A and your what is the concentration of your FC plus, and what is the concentration of FC plus FC, this is shown over here in this A, B, C, D, E, F and G. These are the different points in your cyclic voltagram. So when you're looking at A, what you're having, the highest concentration is basically of your FC plus over here. And so if FC plus is in the highest concentration, then gradually the concentration of your FC increases as you are decreasing the potential. And then gradually you can see how the concentration of each and every component it decreases, and accordingly you will get this particular plot. So this moves up, it goes down, it again comes here and it goes here. So the concentration profiles for Fc plus is given in blue, and for Fc it is given in green as a function of distance from the electrode, that is d which is from the electrode surface to the bulk solution at various points during the voltagram. So why are there peaks in this CV? We saw these peaks, right? These peaks which you are seeing over here, one peak here and the other peak there. So why these peaks are there? So there is an equilibrium between the Fc plus and Fc, and this is described by the Nernst equation, which we had already discussed in the first lecture. So according to the Nernst reaction, there is a 1 electron reduction of this Fc plus to Fc, and the activities are replaced with their concentrations. Here it was actually activity, but now you can replace it with the concentration, because these concentrations are more experimentally accessible. And the standard potential E0 is replaced with a formal potential E0 hash, and n is equal to 1 in this particular case, because you have only one electron transfer. So the formal potential is specific to the experimental conditions employed and is often estimated with the experimentally determined, which is the E half value. So when the potential is scanned during the CV experiment, the concentration of species in solution near the electrode changes over time in accordance with the Nernst equation, because your concentration of Fc plus and your Fc is changing with time. So now then what is going to happen? The volume of solution at the surface of the electrode, which contains the reduced Fc, this is known as the diffusion layer. This continues to grow throughout the scan. So what will happen? This will slow down the mass transport of your Fc plus to the electrode. So when you are scanning to more negative potential, the rate of diffusion of this Fc plus from the bulk solution to the electrode surface will become slower, and this will result in a decrease in the current. And this decrease in the current is what you see over here, because the y-axis is nothing but your current. So this is the decrease in the current which you see as the scan continues from C to D. So now the Fc which is present at the electrode surface is now again going to get oxidized back to Fc plus as the applied potential is becoming more and more positive. Now your potential is getting more positive as it is moving from D to this portion. So at points B and E, what is happening? The concentration of Fc plus and Fc at the electrode surface are equal. So that is as per the Nernst equation. So in this particular case, E is going to be E half, and this corresponds to the halfway potential between the two observed peaks, that is between C and your F. So this is the halfway potential, this particular potential. And this provides a very straightforward way to estimate the E0 dash for a reversible reaction transfer. So the two peaks are separated. Why? Due to the diffusion of the analyte to and from the electrode. So what happens is, if a reduction process is chemically and electrochemically reversible, then the difference between this anodic and cathodic peak potential, which is known as the peak-to-peak separation, this is given by this particular thing, that is delta EP. This is going to be 57 millivolt as per the Nernst equation. And the width at half max of the forward scan of the peak is going to be 59 millivolts. But whenever there is a low barrier to the electron transfer, that is, there is an electrochemical reversibility, the Nernstian equilibrium is established immediately when you are applying any change in the applied potential. But whenever there is a high barrier to the electron transfer, so here the electrochemical irreversibility comes into picture, then the electron transfer reactions are going to be sluggish and more negative potentials are required to observe the reduction or the oxidation reactions, and this will give rise to a very large EP value, or the peak-to-peak separation is going to increase the moment there is going to be an irreversibility, an electrochemical irreversibility in your reaction. So by looking into the cyclic voltagram, you should be able to say that whether it is a reversible kind of reaction which is taking place, electrochemical reversibility there, or is there is a component of irreversibility in your electrochemical reaction. So here the role of scan rate is very important. How you are scanning, what is the speed of scanning? So scan rate of an experiment controls how fast that applied potential is getting scanned. So faster scan rates, it will lead to a decrease in the size of the diffusion layer. So what is going to happen? You are going to observe higher currents. And so this is basically governed by something which is known as the Randall-Sevcik equation. So for an electrochemically reversible electron transfer process involving freely diffusing redox species, you will have this kind of Randall-Sevcik equation, which is going to give you how the peak current, which is this IP value, is going to increase linearly with the square root of this scan rate. So you see your peak current is actually dependent on your scan rate. Okay. So it is going to depend on the square root of the scan rate. So here in this equation, just remember one thing, all the other things are more or less it is constant. So N is the number of electrons transferred in the redox reaction. Then A is the electrode surface area. D0 is your diffusion coefficient of the oxidized analyte. C0 is the bulk concentration of the analyte. So ultimately it is depending, this IP value is depending on your scan rate for any particular material which you are testing, or the reaction which is happening, the electrochemical reaction, what is happening. So now in a reversible process, since the rate of electron transfer is very rapid at the surface of the electrode, the peak potential EP, this is going to be independent of the variation of the scan rate. This is going to be in a reversible process. But the moment you have a quasi-reversible process, this shows limitation of an electron transfer kinetics, and then the peak potential is going to become a function of the scan rate. Now for lithium intercalation reaction which happens, that is basically a quasi-reversible process. Because the cathodic and the anodic peaks, as you can see, it depends on the scan rate. So as you change the scan rate, you will see the position and the value of that peak is going to change. So the CV of a quasi-reversible process, they show a gradual peak shift to higher potential value with an increase of scan rate than one of reversible process, and this is due to overpotential which is developed. So now let's see, to obtain exact lithium-ion diffusivity, you have to consider two boundary conditions, which has to be considered according to the scan rate. So if it is a infinite diffusion process, that's a fast scan rate, in that case it is going to follow this Randall-Sevcik equation which we mentioned. Whereas if it is a finite diffusion process, whereas that means it has a very slow scan rate, in that case the peak current is going to become proportional to your scan rate. So instead of IP being proportional to nu to the power of half, in this case IP is directly proportional to nu. So if you have, so this is basically two different ends of the spectrum. This is how the IP is going to change, or your peak current is going to change. But now if you have different diffusion behaviors induced by the scan rate, then you have a more complicated equation as is shown over here. Need not remember it, but just have in mind that here this beta value, whatever you see over here, is nothing which has your scan rate. Okay, this basically has your scan rate kind of factored into it. And all the other constant values are as same as we had explained in case of the Randall-Sevcik equation. So from this particular slide, what you have to remember is these two equations. This is your when you are having a very fast scan rate and when you're having a low scan rate. So in a battery system, electrochemical reaction occurs in the electrode through consecutive processes. So the current is going to obey a power law. How is that? I is equal to A nu to the power B. Now I is the current, nu is the scan rate, and A and B, these are adjustable values. Now this B is very important. B is the sum of all the Faraday, that is the diffusion control process or the current, and your non-Faraday, which is the capacitive current. So please remember, Faraday are diffusion control, non-Faraday are capacitive currents. So if it is only a diffusion controlled reaction, then the observed current is going to be proportional to the scan rate to the power of half. And this is according to the Randall-Sevcik equation. The capacitive current, on the other hand, which is also known as the non-Faraday or double layer current, in that case, that is going to be directly proportional to your scan rate. So you have to now again, join back all these things. So the capacitive current, it means this is dominantly measured when you're having a fast scan rate. And the diffusion control current is going to be dominantly measured when you're having a very slow scan rate. So the B value of total electrochemical reaction is composed of diffusion controlled and capacitive reaction. And so it is going to have a value between 0.5, which is diffusion controlled, and 1, which is capacitive. So then if you are using this particular equation over here, you are adding, log on both sides. Ultimately, what you get is this particular equation, that B is log I minus log A by log nu. So if you are plotting log I versus log nu, what you have is a particular straight line, and the slope of this particular thing is your B value. So you get the contribution, the non-Faradaic as well as the Faradaic contribution to the current from this slope. So then what you do? So the total current at a specific potential is sum of both diffusion control and capacitive control. And you know that diffusion control is basically this, capacitive control is this. So you just do a little bit of mathematical rearrangement, and what you can get is this K1 nu, which is nothing but current which is attributed to capacitive reaction, and you will get K2 nu to the power half, which is basically the current which is due to the diffusion controlled reaction. So with this, you are able to find out in your lithium ion battery, your material, how much of the current which is being generated is coming from diffusion controlled reaction or from capacitive reaction, and how you can play around with them. So now there are different factors which affect the shape of this CV peaks, as we see. So one is particle size. What happens? Size reduction, it induces an increase in the interfacial area of the particles, so the contact area of the electrolyte, and so it will shorten the diffusion length of Li+. So if you reduce the size, then your diffusion distance decreases, as I mentioned before. So what is going to happen there is this is going to enhance your kinetics of the redox reaction. So the overall peak current will increase at the same scan rate in cyclic voltammograms. So if you have, suppose LFP is LiFePO4, your cathode material, these nanoplates and microplates are having different particle sizes. If you look into the scan rate, what is going to happen? In case of nanoplates, you will find that the current is much higher compared to that in what you see in case of your microplates. So the smaller the size, you find the peak current, it kind of increases. Then there are other factors also like the electrode thickness and scan rate. So the peak separation, as we know, is mainly caused by the following reasons which I've already discussed, but I'm reiterating here. It's the potential drop or increase in resistance due to a slow electron transfer. There is steric hindrance of electrolyte permeation, or there is a porous structure, and there is slow and quasi-irreversible or irreversible electrochemical reactions which happen. And this is what gives rise to the peak separation. So when you have a thin electrode, what is going to happen? The entire portion of the electrode is going to be in uniform state and electrochemically active. So the peak split changes, they are not going to be so large. So that means both the surface and the bulk structure of the electrode have a uniform potential and they are more homogeneous. Whereas the moment you have a very thick electrode, with the scan rate increase, it will show a much larger split in the peak. Why compared to the thin electrode? Because now the lithium ion diffusion from surface to bulk, it will become difficult. So if it becomes difficult, then the bulk potential of the electrode, it depends on distance from the surface, and this will cause a potential drop. And so you can find out that if your electrode is thick, in that case you will find that with the same material, the peak shift is going to be much more. So the delta EP value is going to increase. Then another factor which is going to affect the shape of your diagram is the temperature. So the peak current which arises from a diffusion controlled reaction is significantly affected by operating temperature, whereas those which are arising from the capacitive contribution, they are not dependent on temperature. So the rate of electrochemical reaction depends on lithium ion diffusion in the lattice of the active materials, and this diffusion process is going to be temperature sensitive. So we know that for lithium ion batteries, the thing is this lithium ion diffusion is, there is a diffusion process which is taking place. So the diffusion is anyway dependent on temperature. And so that is why it is temperature sensitive also. So your CV is going to show certain changes with the change in the operating temperature. So when your peak split, it decreases at high temperatures, it indicates that the rate of the electrochemical reaction becomes faster and the corresponding redox peaks can appear earlier. So these are the different factors which are going to affect the shape of your CV. So now this is how the CV is going to look in case of LIB. Now I will again rehash a few definitions because your battery testing is still going on. You just finished the CV part. So now what next? So what are some definitions which I have already mentioned in the first lecture? Just revising that. Terminal voltage, it is the voltage between the battery terminals when load is applied. What is your open circuit voltage? It is voltage between the battery terminals when no load is applied. What is the internal resistance? Overall resistance within the battery, which varies with charge level and temperature and generally differs. It will differ with the charging and the discharging. So, and the battery capacity is what? Amount of the electric charge it can store in a specific condition. It is measured by discharging a fully charged battery through a load at a constant current rate. And capacity of a battery usually depends on the discharge condition. So what are the discharge conditions it will depend on? Discharging current rate, temperature, etc. So why we went through this? Because now when you have your coin cell, you have done the CV, you know what kind of electrochemical reaction is taking place inside your cell or in your material. Then you have to do whether your coin cell is running, it is showing enough number of cycles, and how much of charge and discharge it is able to take in. So how will you do that? So here you can see over here I have given a plot which is basically versus time, voltage, and on the other y-axis what you have is the current. So voltage increases steadily while charging the battery. Okay, during this step, lithium ions, during charging, what is happening? Lithium ions are extracted from the cathode and they intercalate into the anode's graphite layer. So what is happening? The lithium, this cell will be potentiostatically held at 4.2 volts. You see, it is moving from 2.75, it is moving to 4.2 volt, and then it is going to be held at 4.2 volt after it reaches the upper voltage limit. Now, how long it is going to be held? Until the current reaches around 0.4 milliampere, which will correspond to a C rate or a discharge rate of 0.01. So this ensures your battery is now fully charged. So the battery state of charge is right now 100%. So the voltage initially will drop. Now after this your charging step is done and now your discharge is starting. So before the discharge starts, the voltage will drop at the beginning of the discharge step. And why this is going to happen? Because according to the Ohm's law, this voltage drop is delta U, which is nothing but IR drop, and this I and the R is nothing but your equivalent series resistance. So what is the series resistance? It is all the resistance which is coming up from the electrode, electrolyte, electrical contacts. So if you have low delta U, obviously you know that this is going to maximize your output energy E, which can be drawn from the battery. So the limit of a battery's usable capacity is reached when the voltage declines sharply. As you can see over here, the voltage was dropping gradually. Here it started decreasing sharply. So that means at this particular point, you have to kind of stop it. So at this voltage, the state of charge is defined to be 0% and the depth of discharge is 100%. As I was talking to you about the C rate, the term C rate, it will describe how fast a battery is charged or discharged. So here, this particular plot which has been shown, in this case, the rated capacity is 40 milliampere hour at a 0.2 C rate. So this means ideally what you can draw is 40 by 5, that is 8 milliampere of current you can draw for 5 hours from this particular battery whose plot is shown over here. So different batteries will have different C rating, different charge rating, and then depending on that, that is the amount you can have an idea about the amount of current you can draw from the battery and for what time. So now the testing starts with the battery cycling. So batteries, it can be charged faster when you are using the higher C rates. Vice versa, energy can be drawn at a shorter period of time. However, higher C rates, you have to remember, it drastically affects the performance and lifetime of a battery. So that you have to remember. So then what we do is normally when you put this coin cell, you put in a battery tester cycler and you test it. So you do different number of charge discharge cycles and you keep measuring the capacity of the battery. So if your battery is going up to 100 cycles and this is the charge and the discharge, one is green and the other is blue, the charge discharge capacity as you see over here, because of the IR drop, you are seeing a little bit drop in the charge capacity compared to the discharge capacity when you see in the anode form. So what is going to happen is with different cycling, if this capacity just falls like this, that means it has a very poor cyclability. Whereas in this particular case, you are seeing it is more or less it is holding on to your capacity. So that means this particular coin cell material, with whatever material you have made, this is definitely a good material because it is holding on to the capacity after so many cycles of charge and discharge. So now coming to the next category of testing which you will do is basically known as the electrochemical impedance spectroscopy. So this is a very what I should say is a very nice technique to give you a view about the, it's an in situ analysis of the dynamic process which is occurring inside the battery. So you now know how the electrochemical reaction is happening. You know how much stability or structure is having when it's going through the lithium ion insertion, de-insertion, and it is holding on to the capacity. That means the material is definitely able to hold on to the structure. But exact dynamic process, what is happening inside the battery, this particular technique is going to tell you. It's giving you an in situ analysis of the processes which is taking place inside the battery. So it provides a considerable amount of information in a relatively short space of time, and it preserves the integrity of the battery. So it doesn't destroy your battery. So in the EIS, what you do is a small alternating current signal is applied over a very wide frequency range, and the response of your voltage to that, it is measured. So EIS is particularly sensitive to system that contains several impedance elements. So that includes bulk components and interfaces. And so that is why it is very well suited to study a multi-component device such as a battery. Why multi-component? Because you have electrodes, you have electrolyte, you have separator, you have so many electrode contact areas. So this is a multi-component device. So the EIS is a very sensitive technique to study that. So different components and processes within a cell, you have to remember it operates on different time scales. So they have different time constants, and this can be separated very easily in the frequency domain using EIS. That is why this technique is extremely advantageous. So when you go into when you measure an EIS of a particular cell, this sometimes looks like this. So you have a real part and you have an imaginary part. So now what we will do is we'll try and find out, the different how we go about into this electrochemical impedance spectroscopy, the basics of it, and then how it is applied in batteries, and how you go about analyzing this kind of spectra which has come in, or plots which has come in from the EIS spectra. Coming to very basic definitions, because now we'll start with the basics of EIS. So Ohm's law defines resistance as the ratio between voltage and current. Everybody knows that. So this relationship is limited to only one circuit element, that is the ideal resistor. This is an ideal system. So what does an ideal system do? It will follow Ohm's law at all current and voltage level. Resistance value is definitely independent of frequency, and the AC current and voltage signal to a resistor, they are in phase with each other. Okay, the current and voltage signals through the resistor, they are always in phase. So that is the ideal case. But in the real life, what happens? The circuit elements, they are much more complex. So instead of resistance, now we will use the term impedance. Resistance is for a very ideal system, whereas we use impedance when we have a complex or real life system. In a circuit, what we talk as the circuit resistance, we generally give it the term as impedance. So impedance is a measure of the ability of a circuit to resist the flow of electrical current. But impedance, you have to remember, is not limited by the simplifying properties by which the resistance is generally limited. So electrochemical impedance is measured by applying an AC potential to an electrochemical cell, and you measure the current through the cell. So you suppose you are applying a sinusoidal potential excitation. So the response to this potential is going to be an AC current signal. It contains the excitation frequency and its harmonics. So the current signal, it can be analyzed as a sum of the sinusoidal functions. So it's nothing but a sum of sinusoidal functions, which is a Fourier series. So electrochemical impedance is normally measured using very small excitation signal. And why this is so? Because then your cell's response is going to be pseudo-linear or linear. And in linear system, what happens? The current response to a sinusoidal potential will be a sinusoid again at the same frequency, but it is just going to be shifted in phase. So it becomes much easier for you to study. It is much more simpler, but it has all the different intricacy which you want to study in that particular material. It has all the information of that. So how the sinusoidal current response in a linear system is going to look? The excitation signal is expressed as a function of time. So it has a form Et is E0 cos omega t, and where omega is the radial frequency. Whereas when you have this potential is applied, in that case, how your current signal is going to look, the current is going to look, it is going to have the same frequency as you can see over here, but there is a phase shift. So you can see this phase shift which has taken place. So the relationship between this radial frequency omega, which is expressed in radians per second, and frequency f, we all know, which is in hertz, which is the normal frequency unit which we all are very we commonly hear it, which is hertz, which is per second. So omega is 2 pi f. So how do you measure impedance? So the CIS can be measured either in potentiostatic, which is constant voltage form, or in galvanostatic, which is constant current mode. So as I mentioned before, we normally do a galvanostatic mode, which is a constant current mode. So in potentiostatic mode, what you do is the voltage is applied at each frequency and the resultant current is measured. This is common. And current responds at the same frequency as the applied voltage, but it may be shifted in phase. So in order to ensure a steady state, the CIS is generally carried out with a very small potentiostatic signal amplitude of 10 millivolt so that the cell response is pseudo-linear. Okay. So if a system is nonlinear, the response contains harmonics of the input signal frequency. So in order to accurately perform EIS on a cell during cycling, you have to give a rest phase or an open circuit voltage period so that the cell voltage, it will not vary significantly during your measurements. That is very important. So you are kind of having a constant voltage. Similarly, additionally, you have an additional rest period, and open circuit is often implemented following the impedance scan. So the cell can recover from any changes which occur during the EIS run prior to continuing with constant current or constant voltage cycling. So you always have to give a little bit of rest period. So you give a perturbation, a rest, let the material come to kind of equilibriums in, and then you start studying it. So this slide I will not say because this is all what I have explained below. So what you have is basically ET giving you E0 sine omega t. And then in a linear system, this response signal or the current is shifted in phase, as I said, and it will have a different amplitude than your I0. So your IT will be now I0 sine omega t plus phi. So it's simple mathematics. So an expression analogous to Ohm's law, it will allow us to calculate the impedance of the system. This impedance is generally given by this Z or Z. ZT is nothing ET by IT. And ultimately what you have is Z0 sine omega t divided by sine omega t plus phi. So now you have to go into the complex plane with Euler's relationship, which says that exponential j phi is nothing but cos phi plus j sine phi. So if you apply this to the impedance, and then you can represent this impedance as a complex number. So zt is nothing but z0 exponential j phi. So it is z0 cos phi plus j sine phi. So this is the most important relationship which you have to remember. So this j value is nothing but square root of -1, which is nothing but the imaginary plane. So a generated impedance spectrum, it will consist of resistive and reactive components. So the resistance here is made up of electronic as well as ionic resistance. So the most common form of plotting impedance data is a Z star complex plane plot of Z double dash against Z star, Z hash on linear scales, and this is known as the Nyquist plot. So presenting data in this way displays the resistance, that is along the real or the x-axis, and the reactance including capacitance along the imaginary y-axis. So your x-axis is the real axis, whereas your y-axis is the imaginary axis. So if you look into the plot, now you'll understand what I'm trying to say. So here your y-axis is your real z value, whereas the x-axis is your real z value, and whereas the y-axis is the imaginary value. So if the real part is plotted on the x-axis and the imaginary part on the y-axis of a chart, we get the Nyquist plot. And in this plot, the y-axis is negative, and each point in this Nyquist plot, what it represents is each plot over here, what it represents is the impedance Z at any one frequency. So on the Nyquist plot, the impedance can be represented as a vector of length Z. And then the angle between this vector and the x-axis is commonly called the phase angle or phi. Phi. So, but this Nyquist plot, it has one major shortcoming. So when you look at any data point on the plot, you cannot tell at what frequency. Yeah, you won't be able to tell at what frequency that data was recorded. So that's a very big problem. So whenever you have the Nyquist plot, what you have, you know the imaginary axis, you know the real axis, but you don't have any idea of the frequency. In the instrument, when you measure, that frequency will be there, but looking at the Nyquist plot, you won't be able to tell me that what is the frequency in which that particular point data has been collected. But you have to know that the low frequency data, they are on the right side of the plot. So in this part, it is the low frequency data, whereas this part is your high frequency data. And why this is so? This is because the EIS data, the impedance usually falls as your frequency gradually. Okay, sorry for the interruption. So there's some interruption at this end. So the Nyquist plot, it results from the equivalent circuit, and the semicircle is characteristic of a single time constant. So electrochemical impedance plots, they often contain several time constants, and only one portion or more of semicircles are seen. So in a Nyquist plot, you are able to see, different semicircles, and this different semicircle correspond to different reactions which are occurring at different time scales. Because they're dynamic process, it is going to give you an idea of all the different processes which are taking place inside your coin cell in situ when actually the movement of your lithium ions are taking place. So another popular presentation, so that is the Nyquist plot. Then there is another kind of representation of the EIS data, which is known as the Bode plot. So the impedance is plotted with log frequency on the x-axis, and both the absolute value of the impedance and the phase shift is done in the y-axis. So Nyquist plot and Bode plot, please remember, they represent the same results. But unlike the Nyquist plot, the Bode plot explicitly it will show frequency information. So the small impedance is present in presence of large impedance. It can be identified very, very easily in case of a Bode plot. So as you can see in Bode plot, what you find is you will get the information of your frequency, as well as you will get an information about all the different processes which is taking place in the cell. So that is an advantage of the Bode plot. But most of the research papers, you'll find that they work on the Nyquist plot. So now you have your plot, that different plot as I showed, but you have to do some fitting to find out, what are the different processes which are taking place in your cell. So you have to do a fitting with an equivalent electric circuit model. So what are the different things you will use? The common electrical elements like resistors, capacitors, inductors. So most of the models, it will contain a resistor and it will model the cell's solution resistance. So what is resistor? The impedance of a resistor, it is independent of frequency and has only a real component. So remember, there is no imaginary component for a resistor. So because there is no imaginary impedance, the current through a resistor is always in phase with the voltage. All this becomes very handy when you are actually trying to fit your EIS data with an equivalent electric circuit. For an inductor, what happens? The impedance of an inductor, it increases as the frequency increases. So inductors have only an imaginary impedance component. So as a result, an inductor's current is phase shifted by 90 degrees with respect to the voltage. So this is all your physics knowledge which is coming into the picture. Then you have capacitor. The impedance versus frequency behavior of a capacitor is just opposite to that of an inductor. So a capacitor's impedance, it decreases as the frequency is raised. So capacitors will also has only an imaginary impedance component. But you have to remember the current through a capacitor is phase shifted minus 90 degrees with respect to voltage. So for an inductor, it is plus 90 degree phase shift, whereas in case of a capacitor, it is a minus 90 degree phase shift. Then you have something which is known as Warburg impedance. So this represents the resistance to mass transfer or the diffusion control. So the impedance depends on the frequency of the potential perturbation. So at high frequency, the Warburg impedance is going to be relatively small, since diffusing reactants don't have to move very far because the frequency is very high. But at low frequency, the reactants have to diffuse further. So now in this case, you will find lot of contribution from the Warburg impedance. So on a Nyquist plot, the Warburg impedance, it generally appears as a diagonal line with a slope of 45 degrees. I'll show that plot. I'm coming into next slide. And then you have something which is known as the constant phase element. So capacitors in EIS experiments, they often do not behave ideally. Instead, they will behave like a constant phase element. So these are nothing but very imperfect capacitors. So capacitors, as I said, will normal capacitors or true capacitors will have a minus 90-degree phase shift. Whereas in case of a constant phase element, that phase shift is not exactly 90, it will be a little less than that of 90. So you have these different mathematical forms, which I will not obviously, read out over here, but you can go through the slide later on. So these are the different mathematical forms of impedance with these different circuit elements. What we are more interested in is how by combining these different circuit elements, you are able to generate a plot which looks like the EIS plot which you have, which you will get through your experiments. So now for that, we have to first learn that how it will look when you are having impedance in series and how it looks when you have impedance in parallel. So impedance in series and impedance in parallel follow the same mathematical representation of resistance. So when you have impedance in series, it is just a numerical addition of that. Whereas when you have in parallel, it is 1 by Z1 plus 1 by Z2 plus 1 by Z3, and the pictorial representation is almost similar to that what you have in case of resistance. So what is the common equivalent circuit model that you have to know? For a resistor, you have this representation for a resistor. And in this particular case, a resistor, it will show, and you will find that when you are talking about the resistor, it has right there on the x-axis. Whereas in case of a capacitor, the capacitor value will come along the y-axis. It is shown in red over here. Okay, and the capacitor, pictorially it is represented in this particular form. The circuit representation is like this. And when you have a resistor and a capacitor in series, if you do the simple mathematical calculation, that is ZR plus ZC, which is R plus 1 by JWC. So this is where basically your resistor and capacitor is going to look on the Z plot and the Z double hash plot over here. So the imaginary and the real plot, if you plot this, a resistor and capacitor in series, this is how the representation is going to look. But this is not how your EIS spectra looks. So we have to add in something more. So now if you have a resistor and capacitor in parallel, in that case what is happening? You have, when you do the simple mathematics which is shown over here, you can go through it in leisure, you have something which is basically, it looks like the equation of a circle. So in this case, what you have is a semicircle, a perfect semicircle. So now you can see that this looks more like your EIS spectra. So this is nothing but a simplified Randall's cell. This is one of the most common cell model. It includes a solution resistance, a double layer capacitor, and a charge transfer or a polarization resistance. So what you have over here, you have the resistance of this cell over here. You have the resistance which is coming due to charge transfer, and you have a double layer capacitance. So this particular thing, so when you have this kind of a model, this is nothing but a simplified Randall's cell. Now with a simplified Randall's cell, if you are having, another resistance which is added to it along with this particular Randall's cell, then this R sigma value is nothing but the resistance of your cell material. So your electrode, your electrolyte, so all these different materials, this was going to give rise to some kind of resistance or impedance. And this is basically this R value over here you see in the plot. The rest of it you have to fit using this particular circuit, equivalent circuit, and this is going to give you this semicircle. So far so good. Now what is going to happen? Then you have that 45-degree angle straight line coming in. So this is your mixed kinetic and diffusion control. So when your omega is very small, that means your frequency is very less. In that case, when you do the entire mathematics as shown over here, what you find is equation of a straight line. So this is what you will see, a 45-degree angle. And here is that Warburg impedance. This Warburg impedance is nothing but giving you your kinetic and diffusion control. So at the low frequency range, you see this the straight line which is coming with a slope of 1, so it's a 45-degree angle. Whereas when your omega is very large, that is your frequency is very high, in that particular case what you have is this particular equation over here, and in this case when you fit this together with all the other equations you had, what you have is this particular plot as you have shown over here, this EIS plot. And this definitely looks so much like the EIS spectrum, which actually you will receive after you do your experiment, which you will get after doing your experiment. So this entire maths has to be done. So at high frequency range, cell process is determined by charge transfer. At high frequency means in this region, it is all the charge transfer. At the low frequency range, cell process is determined by mass transfer or diffusion as is shown over here. And this R omega, R charge transfer, all your capacitance values and sigma, they can all be calculated from the Nyquist plot. So you are getting an idea of all the different processes which is taking place in the cell in situ, and dynamic processes in the cell. So now you have to do the modeling. So electrochemical cells can be modeled as a network of passive electrical circuit elements. The network is so-called an equivalent circuit. And the EIS response of an equivalent circuit can be calculated and compared to the actual EIS response of the electrochemical cell. And if it matches, then you say that this model is fitting. So how you do? You get your experimental data, you develop a possible equivalent circuit by looking into it. You have to mix and match. Now it is mostly done using software. You adjust it until it fits well, and parameters related to different elements you will obtain. So the common softwares which are used for EIS modeling are ZSymWin, ZView or Gamry Echem Analyst. So these are the different common software which are used when you are having your EIS spectra. You will use this software and you will get your fitting. So this is an ideal spectrum This is how the ideal spectrum is going to look with equivalent circuit. If you're fitting your circuit in this way, it should look like this. So with decreasing frequency, the first feature is a non-zero ohmic resistance, as you see over here, where the spectrum interacts with the real Z prime axis at high frequency, and this is represented in the equivalent circuit by a resistor which is RHF, which is resistance at the high frequency region. Then followed by that, what you have in a lithium-ion battery, when we take an EIS spectra, this somewhat looks like this as shown over here. Circle, and then you have a straight line. So all these different regions, they are actually processes which are taking place in different time scale. So these are A, B, C and D regions. So what is happening? So lithium ion migration through the solid electrolyte interface layer, activation kinetics in both negative and the positive electrodes, double layer effects at the interfaces of electrolytes, and lithium ion diffusion processes in the active material of the electrodes. So these are the different processes which are taking place, and then you will make a equivalent circuit as shown over here. And this equivalent circuit, when you do the entire calculation, which is obviously being done by the software, it is going to generate this particular EIS data. And then you know the value of each of these different circuit elements, and this is basically the process which is taking place in your battery and in your coin cell. So what does the region A represent? Region A is represented by a single ohmic resistance, RO, and this area corresponds to the battery ohmic losses. So includes resistance from the current collectors, active material, electrolyte, separators. So when your battery is not running, at that particular point only this kind of resistance are already present in your cell. So that is because of the existence of the cell, the materials you are having in the cell, that gives rise to this resistance. Then you have a high frequency region B, and this B is represented by the solid electrolyte interface resistance or RACI, ACI layer capacitance, CEI, and a fractional element which is delta alpha 1. It corresponds to the lithium ion migration through the ACI film layer. So this particular equivalent circuit, it represents to this region, that is region B, where your ACI is forming. Then you have a medium frequency region where you have a semicircle which is having a much higher radius. So medium frequency region C, this is represented by the charge transfer resistance which occurs, which is RCT. So in this case, a double layer capacitance is there, as you can see, the CDL. And then again, you have a very small fractional element, delta alpha 2. This corresponds to the activation kinetics and double layer effects at the interface of the electrolytes. So this particular circuit region, equivalent circuit region, it corresponds to your medium frequency region C. And then you have a very low frequency region D. This is represented by the Warburg element, it is shown over here, the ZW, and a fractional element which is delta alpha 3. This corresponds to the lithium ion diffusion process in the active material of the electrons. So all what is happening inside your coin cell, all the different processes, they are accounted for in the EIS spectra. And with a very good fitting, you are able to find out exactly what is happening, how much of the resistance is coming due to the ACI formation, how much is the charge transfer, whether by changing or changing the geometry or putting in dopants or adding in defects, whether the charge transfer is improved or not, that will be given by the EIS spectra. So immediately you will find a decrease in the RCT value, which means your charge transfer process is becoming more efficient, your kinetics is improving, and then basically this region will show you how the diffusion of the lithium ion is taking place. So from that you are able to get in the speed of the lithium ion diffusion. So now coming to one very important point, which is battery life. So most lithium ion batteries, it should not be charged at ambient temperatures below 0 degrees or above 45 to 50 degrees. Why? Because charging at high temperature, it decreases your cycle life and it also may present a safety hazard. Then charging at low temperatures may lead to the growth of lithium metal dendrites, which can result in an internal short circuit and destroys the battery, and it can potentially cause fire. It's a fire hazard, definitely, because you have liquid electrolytes, most of which are volatile. So the moment a short circuit happens, there's a thermal runaway happening and then it catches fire. There's a very big hazard. Then batteries should be stored at or near room temperature at 25 degrees centigrade, and the state of charge should be 20 to 40%. You shouldn't store batteries which are fully charged or in elevated temperatures. Why? Because this will put a stress on the cell and it is going to reduce the battery life, and it is going to increase the amount of energy available for thermal runaway should an accident occur. So if you want to extend the life of a battery, it's very important that you operate the battery at very ambient temperatures. So there are different degradation mechanisms which take place in the battery. So one is obviously electrolyte decomposition. When an electrolyte decomposition takes place, the effect is you will have loss of alkali metal. That is going to be deterioration of ionic transport, and the result is going to be capacity fade, impedance rise. And the same thing you will observe if there is a lot of solid electrolyte interface formation, if there is a binder decay, or there is a particle contact loss. In all these cases, you will find a loss of the active electrode material, and there is going to be a capacity fade and a rise in the impedance in the battery. Then in many other cases, what is going to happen, you can have a metal plating happening, that is the lithium is going and forming a plate. Then you can have transition metal dissolution, that is your cobalt or lithium cobalt oxide, the cathode material, the transition metal completely is dissolving. So you will have a loss of active electrode material. So there is going to be a capacity fade. You can have structural disordering or unfavorable phase transitions take place, like I said about the layered to the spinel phase transitions. In that case, there is going to be loss of active electrode material. Again, you will find a capacity fade. If you change the porosity, then there is going to be deterioration in ionic transport. Suppose the porosity decreases, then the ionic transport is hindered. So there is going to be an increase in the impedance. You decrease the electrode surface area, again, there is going to be an increase in impedance. Oxidation of the conductive additive, if it takes place, then again there is going to be an increase in the impedance. If you corrode your current collector, in that case also you will find the resistance increasing. So there are various degradation mechanisms which occurs in the battery. So that has to be by these different techniques, by these different testing techniques, you will able to find out what exactly is going wrong with your material which you are testing. So now a small bit of idea about no, I think it's already 5:25, so I'll not go into the capacitor and the fuel cell today. I think I will stop the class here today because it will not be, there's not enough time to talk about these other energy storage techniques. So what I'll do is I will stop it over here today. And if there are any questions, I will take up right now. And then in the next class, which is going to happen on next Thursday, I will continue with the supercapacitor and the fuel cell. So I'll just sum up for you whatever I have taken up in today's class. So today we have discussed lithium ion battery anode materials particularly. With that, actually, we finished the electrode materials part. So both the cathodes, which was covered in the last class, followed by anodes, which we have covered today. And then we spoke a little bit about how you fabricate these cells. And after the fabrication, then the next step in battery is testing. So what are the different testing techniques which you use for the electrochemical testing of your cell, test the electrochemical performance of your cell. So for that, what we do is we do a CV measurements we do, then we do battery testing, which is the cyclability measurements, how your capacitance is going to change, or the capacity of the material is going to change with repeated lithium insertion and deinsertion. So that we test. Then followed by that, what we do is we do an electrochemical impedance spectroscopy, which we covered in some detail to know the dynamic processes which are taking place in the battery. Then we saw how we can extend the battery life. What are the different factors which actually, kind of decrease your battery life? How you can enhance performance by not, doing certain things with your battery. So those are the things which we have covered. So with this, we have almost come to an end with the battery part. And other two energy storage technologies which we will talk about is the supercapacitors and fuel cells, though not as exhaustively as we covered batteries, and that we will do in the next class. As of now, I don't see any question coming in. So I think we stop the class right now, and a very good evening to all of you all.